Okay, topic 9 is on isomerism. You might have learned some of it in secondary school, so let's try to look at what might be familiar to you. Most of you, from this particular learning objective, you would have learned structural isomerism, but please take note that structural isomerism is an obsolete term. So for H2 chemistry, we are using constitutional isomerism in place of structural isomerism. Okay, so we'll take a look at what, if you forget about what constitutional or structural isomerism is, we'll take a look at that. And you're going to be introduced to stereoisomerisms. So in particular, cis-trans isomerism is something that you will encounter. But take note from your syllabus outcome that you do not need to know the easy nomenclature. Okay, so but this particular easy nomenclature will be taught in H3. Yeah, although I mean it's not something that is very difficult. Okay, so in the course of the tutorials you might hear me talking about it, but yeah, you might not need to pay too much attention to it, but it's good to know for learning purposes. Okay, so I will just jump straight into the introduction. Yeah, so basically isomers they share the same molecular formula. Yeah, but they differ in the arrangement of the atoms. So what do we mean by they differ in the arrangement of the atoms? So for example, if you look at a formula written in this way versus written in this way, or maybe let's say written in an ugly way like this, 1 2 3. Oh, sorry, I think I drew one more carbon. Okay, maybe written in an ugly way like this. Okay, or maybe even written in a way like this. Okay, you may be thinking that they represent different things. Okay, but we need to be aware that when we draw skeletal structure, all the edges, not edges, all the corners, they actually represent a carbon. Of course, you have to add on the necessary number of hydrogens. If you just count the number of missing sigma bonds. So if you need a bit of revision, like for example, in this particular corner, if we have a C here, there are 2 sigma bonds here, so there will be 2 H's here. Okay, and of course the C right at the end, there's only 1 sigma bond, so there will be 3 H's. Okay, so no matter how we draw it, we actually end up drawing butanes. Okay, we just the structures just differ in what we call the conformation, but conformation is not in the H2 curriculum, so you might not want to be too worried about it. Okay, now the reason why all these forms right are the same thing, right, is because for single bonds there will be free bond rotation. Okay, so there's free bond rotation around the CC single bond. So that is why a straight chain molecule, right, we tend to say that it has a greater degree of freedom as compared to something that is, let's say, cyclic. Yeah, because when let's say you join the 2 carbon at the end together, right, they will not be able to take on a more bizarre form of arrangement. So for example, if I have something that is straight chain, I can be straight or I can be like this. Yeah, if I want to. Okay, but if a molecule is in the cyclic form, or you learn it in introductory organic chem as the alicyclic form, they are not able to twist and turn too much. Yeah, so whenever you have a ring system, you are restricting the degree of freedom being given to the molecule. Yeah, so in that sense, it's not able to showcase a more variety kind of arrangement, or what we call conformation. Okay, but if you are really interested in that, then you could consider taking an H3 in your JC2. Then you'll learn a little bit more about it. Or if not, you can just read the textbook, which I'm going to provide you for reading. Yep. Okay, so you have the different conformation of the pentane molecule, and then if you draw all the bonds, you realize that actually there's no difference if you draw them straight chain. Okay, so for example, if I'm going to look at this particular structure, from the longest chain is actually 1 2 3 4 5. So this is the longest chain, and then for in this case is 1, 2, 3, 4, 5. Okay, so same case goes for this 1, 2, 3, 4, 5. So you notice that I do not need to lift my pen in order for me to go from one end to the other end. Yeah, so if I do not need to lift my pen, that actually means that all these structures are the same thing. So they represent the same pentane molecule. Okay, however, if I'm going to swap these two, this particular methyl group and this H, for example, right? Okay, so I'm just going to draw it out. H3C, CH, H, and then CH, CH3, and then CH, H, H. Okay, so I'm going to highlight. Can you see? I swap the two groups. Did you realize that now when I go from one end to the other end, it's no longer 5 carbon? Okay, so let's try. This is 1, 2, 3, 4. And then you'll be saying, I can go to the fifth one like this. No, you cannot go like this. You have to move along the sigma bonding framework in order to tell whether they are isomers or not. Okay, so I have to move along the sigma bonding framework. So 1, 2, 3, 4. Okay, then some of you might say, you can go back and then move down. Okay, so that's considered cheating. Okay, so you can't do that. Okay, so in this case, the longest chain is 4 carbon. So we call this compound 2-methyl butane. Okay, but it's no longer the pentane family. Okay, so that is how you identify isomers. So take note of the little tricks or some of the strategy along the way, which I will showcase to you how to identify isomers. Do not be tricked by the way the structures are being drawn. Okay, and we call this, I think in secondary school you learn it as structural isomerism, but over here we call it constitutional isomerism. Okay, so we call this constitutional isomerism. Okay, so we're going to talk about constitutional isomerism in the second section. I think earlier on I've illustrated using pentane versus 2-methyl butane. So I think you have a rough sense about things. Okay, so I think they illustrated the examples here as well. So if you take a look at this example, pentane, I go from one end to the other end. 1, 2, 3, 4, 5. Okay, so in this case, it's an isomer because the longest chain is 1, 2, 3, 4. Okay, or you can look at it as 1, 2, 3, 4. Okay, it doesn't really matter. Okay, so I'll just go straight chain. And then for 2-methyl propane, 1, 2, 3. So that's the longest chain. Or I can look at it as 1, 2, 3, which is the longest chain. Okay, so all these, we say that they are isomers or constitutional isomers of one another with the molecular formula C5H12. Okay, so constitutional isomer with the molecular formula C5H12. Okay, yep. So they have different IUPAC name. Do not, again, let me just stress on this. Do not be too stressed over naming. Over time, you will just get used to it. Okay, so there are constitutional isomers with different position of the same functional group. I'm sure you will encounter this in introductory organic chem. So pens 1 in. So this is where the CC double begins from the first carbon. Okay, some of you actually ask me why is it pens 1 in and not pens 2 in. The reason is because you always name it with the smallest number. So in this case, the double bond is between carbon 1 and 2, so we give it the smallest number, so we call it pens 1 in. The other one is called pens 2 in because the double bond begins with carbon number 2 and ends with carbon number 3. Okay, so that's why we call it pens 2 in. Some of you might ask, what about something like this? Can I call it pens 3 in? Okay, so as I said to you, to some of you during the tutorial, people will laugh at you because if I number from left to right, the smallest number, of course, is 3 to 4, so that's the double bond. But I don't have to number it this way, right? Because I can get a smaller number by going from right to left. Okay, so in this case, I will still call it pens 2 in, and they are the same compound. Okay, let me repeat. The one I'm going to circle in green, both of them are the same compound. Okay, they are not isomers. but pens 1 in and pens 2 in are isomers by virtue of the fact that the position of the CC double bond is different. Okay, so if I have more functional groups, then the possibility will increase until you cannot get hold of it. Yeah, so it's going to be difficult if we increase the number of carbon and the functional group. Okay, so rest assured that we will not be asking you to draw isomers after isomers. Okay, we'll just test you enough to understand that you are aware of the presence of isomers. Okay, so do not be too worried about it. Okay, so ring system, you can also have isomers. I think I don't think this needs further introduction. So if I'm going to color code the OH, okay, over here, right, with orange, and then you realize that the BR in this case is bonded to the same carbon, and then the other BR is bonded to the other carbon, the second carbon. The next BR is bonded to the third carbon. The fourth BR is bonded to the fourth carbon. The next BR is bonded to the fourth carbon. Yeah. Okay, so isomerism exists in the ring systems as well. Okay. For constitutional isomers, it is also possible for you to have different functional group. I don't think this needs I don't think this is anything new to you, because if I'm going to give you the formula C3H6O, okay, you realize if you remember from my earlier video on topic 8, right? Or rather, it might be the review of the in-class exercise, right? I did mention that if you compare with your alkane formula, so let's say if I have 3 carbon over here, so the maximum number of hydrogen I can take for a 3 carbon unit will be 8. Okay, CnH2n plus 2 is the formula of alkane. So in this case, the maximum number of hydrogen that a 3 carbon molecule can have will be 8. Okay, so I will compare this with C3H8. Okay, so if you scrutinize the structure, right, the one given to us over here has 6 hydrogen, but the alkane version has 8. So there is actually a reduction of 2 hydrogen. Okay, so you might realize that for every reduction of 2 hydrogen, that actually means that it can lead to a formation of a double bond. Okay, so if you just do simple arithmetic, you will understand why. So for example, if let's say I have propane, for example. Okay, let's say I have propane. For every double bond or CC double bond I'm going to form, right? Okay, is it surprising that I should be losing these 2 H's? So if I form one CC double bond, I need to lose 2 H in order to form a pi bond between the 2 carbon. Okay, over here. Yeah, and that also applies to CO double bond as well. So let me just illustrate with another example. So for example, if I'm going to have a OH here and then an H, right? Okay, so if I'm going to form a double bond here, as in the case of propanol, okay, do you actually notice that I'm removing one H? Okay, and I'm removing another H as well, and then I will in turn form a new bond over here. Yeah, so you can visualize it such that for every new double bond I'm forming, I need to remove 2 H from the system. Okay, so it shouldn't come as a surprise. So from here, you realize that if I have a formula C3H6O, I should have a double bond somewhere. Yeah, so if you try to draw the isomers, you will end up with propanol, with a CO double bond right at the end, and then why is it an aldehyde? Because over here, this is a H. So if you recall what I mentioned to you in class, if the N is a H instead of alkyl group, and the other side is an alkyl group, we call this an aldehyde. Okay, so the other one we'll call it a ketone. Okay, and with a CC double bond as well over here. Oh, sorry, CO double bond. Okay, and then of course it is also possible for me to arrange the molecule such that I'm getting a CC double bond somewhere. Okay, so in this case I can get a CC double bond like this. So this is called This is an alkene as well as an alcohol. So it has two functional groups, which is quite interesting. Okay, and if you kind of recall what I mentioned to you earlier on as well, if you reduce by two H's, that also means that I can join up the two ends. I don't know whether you remember that. Okay, so let me just erase this and I'm just going to show you again. Okay, so let's say I have a propane. Same thing, I have a propane over here. Okay, if you recall what I did earlier on, to form a CC double bond, I will remove two H and then join them up with a new double bond, right? Okay, okay. What about joining both ends together? Okay, to form a cyclic compound. Okay, so same thing, I will remove a H from one end and I remove the H from the other end. Okay, then over here I'm going to draw an ugly structure to join up both ends. Okay, of course this is extremely ugly, so if I'm going to draw it out nicely, it will look like this, a triangle. Of course this is a skeletal structure. Can I draw it in the displayed formula? Yes, I can. I just need to do it like this. C, C, C. Okay, H, 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 and H. Okay, similar. Okay, so I hope you do recognize this interesting strategy to I don't know how you want to put it to help you determine the total number of constitutional isomers or in the future is going to be very useful for you in structural elucidation. Okay, this strategy of determining the number of double bond equivalent or the number of rings. Yeah, so maybe just let me repeat. If I have two less H, okay, compared to an alkane, that means that I will form either a double bond or a ring. It's either or, not both. Okay, yeah. We're gonna move on to further examples. So yeah, so there are a lot of examples here. I think you can take some time to look through. Yeah, but just be a little bit careful that sometimes you can have the same molecular formula but different functional group. So for example, in this case, it's an alkene, but the isomer is actually an alkane. Okay, in this case, it's a cycloalkane. Okay, and then for the second example, one of it is a carboxylic acid, whereas the other one is an ester. Okay, then for the third one of it is an alcohol. Then the other one is actually ether. Okay, and ether is actually an interesting functional group, but it's not in your syllabus. Okay, so maybe just let me emphasize that this is not in syllabus. Okay, but you'll see it appearing. You'll see it appearing on and off lah, on and off. Okay, either as solvents or maybe in one of the products to some reactions, but don't need to be too worried about it. Okay, and then okay, 2.4, I don't want to go into details because we all have our own ways of doing it. Yeah, so to deduce the possible number of stereo isomers, well, I mean, you can follow this. This is just one way. Okay, so later on when I go through the exercise, I'll just show you how I will go about doing it. Then you need to find your own voice. Okay, your methods might be different from mine. Your methods might be different from your friends. It doesn't really matter. Yep, okay. I'm going to just straight away, yes. So what I have shared earlier on, right, over here, okay, over using this whole technique, okay, is known as degree of unsaturation. Okay, over here, degree of unsaturation, or the Americans actually call it index of hydrogen efficiency. Okay, yeah, it's a very important skill set for you to know, but it is not in the curriculum. It's not required by your curriculum to know it. However, as I said to you just now, it's a very useful tool for you in JC2, especially in structural elucidation. Yeah, if you need to do structural elucidation, you'll find that this tool is wonderful and it will help you a lot.
especially in JC2 lah, when the questions get really complicated. Yeah, so may I urge you to spend a bit of time to read through the page. But if you feel that it's too cumbersome, then it's fine, because degree of unsaturation is actually a tool that is very intuitive. Okay, sometimes people develop, or sometimes you know it without even knowing why. Okay, so I don't think you should be too worried about it. Let's say you don't get it at this stage. Okay, so after promos, or even like after you're more familiar with organic chemistry, if you feel that you want to pick up a little bit of extra skill sets, yeah, you can just read it again. Okay, if not, then I don't think this particular page should bother you. Okay, we'll look at exercise 2.1a, which reads how many constitutional isomers are there in C4H10O. Okay, so I'm going to use a blank page to showcase to you how my way of doing, so you see whether it works with you. Okay, now to me, right, the easiest way to do it is to start off with the straight chain. Okay, which means the carbon chain. Okay, we need to get the formula correct first. So it's C4H10O. Yeah. So if you recall a little bit about what I said to you just now, it will be good to look at the ratio of the carbon to H to check whether it matches with that of alkane. So again, this is CnH2n plus 2. Yeah. So since it matches with that of alkane, then you will know that it's saturated. Okay. Yep. So we're just going to try to work it out. Okay. And you might want to hear me quite closely, because I'm going to showcase to you some of the thought process. Okay. Now the easiest way is not to do this. A lot of students will do this and then blah 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 like this. Okay. To me, this is a bit complicated. So I think this is a good entry point to test your capability of drawing skeletal structure. Okay, because if you're able to do that, then I think you can answer for all questions. Okay, so I'm going to show you how I'll do it. First, I will draw a straight chain. Okay, so that's 4 carbons. Okay, so if you need numbering, I can do it over here. Okay, so this is just simply the carbon chain. I haven't even insert oxygen yet. Okay, then next I'm going to do branching. Okay, so I'm going to do branching. And then did you realize that that's it for 4 carbon? You can't do anything else. Okay, if you don't believe me, you can try. You can't do anything else. You cannot have a ring, because remember, every time you form a ring, the degree of unsaturation will increase by 1, and or rather, the number of hydrogen will actually decrease by 2, but in this case, I have 10 hydrogens, so you cannot form a ring. Okay, so I'll leave you to think about how else you can arrange them, but I don't think, and it's not possible for you to have other form of arrangement. Okay, so basically just straight chain and then a branch. Yep, so that's number 1. Okay, number 2. Okay, I'm going to simply mentally assign the OH group, okay, to the relevant carbons. Okay, so what do I do? Okay, so I'm going to do this. If OH is in carbon number 1, it will be different from when OH is at carbon number 2, right? Would you agree with me on that? Okay. What about OH at carbon number 3? Then we say, no, the OH at carbon number 3 will be the same as the OH at carbon number 2. And then obviously I'm not going to showcase for OH at carbon number 4, right? Because it will be the same as the OH at carbon number 1. So in this case, I'm going to have 2 OHs. Okay, 2 unique alcohols with a straight chain. Yeah, would you agree with me on that? Okay, yep. If you need confirmation, no problem, just draw it out. Okay, so I'm going to draw the one with carbon number 1, and then I'm going to draw the ones at carbon number 2. Okay, then next we'll follow the same thought process, and then we'll check it out. Okay, How about I put an OH at carbon 3? Okay, it will be a unique structure, right? And you notice that this particular structure is symmetrical. So regardless of whether I put it at carbon 3 or 4 or 1, actually it's the same compound. Okay, don't believe? Please try it out. Okay, so I'm just going to put it at carbon number 3 as a unique structure, and then I'm going to put it at carbon number 2. Okay, so I'm going to draw it out. At carbon number 3, this is what I will get. And at carbon number 2, this is what I will get. Okay, and as a whole, the total number of constitutional isomers with alcohol as a functional group will be 1, 2, 3, 4. Okay, but not to forget, this is just alcohols. Okay, it is possible for me to have another functional group. Okay, you were told over here you can have an ether. Okay, either OH or ether. Okay, so that means that I'm going to use a different color ink. That means that I can actually insert, okay, my O, right, between two carbon. Because remember, an ether is where the O is inserted between two carbon, right? So let's try. Okay, can I insert the O between carbon 3 and 4? Yes, I can, right? Because if I insert the O between carbon 3 and 4, I'm going to end up with this structure. Okay, so let me number it. 1, 2, 3, 4. Okay, can I insert an O between carbon 2 and 3? Yes, I can do that, right? Because if I do that, I'm going to end up with this particular structure. 1, 2, 3, 4. Agree? Okay, so that adds 2 more isomers to my list. But let's not forget, we have a branch version. Okay, so let's try to do that for the branch version. Okay, can I add an O between carbon 2 and 3? You realize that if I do it between carbon 2 and 3, it's the same as between carbon 1 and 2 and between carbon 2 and 4. So no difference. So let's do it for carbon 2 and 3. So I'm going to end up with this particular structure. So that's 1, 2, 3, and 4. Okay, so that add one more to the list. So the total number of isomers I'm going to get for ether will be 3. The total number of isomers I'm going to get for alcohols will be 4. So 4 plus 3 will be 7. Okay, so that's the total number of constitutional isomers I will get for the formula C4H10O. Okay, if you want to challenge yourself, okay, you can try to draw for C5H12O. Trust me, you're going to end up with a lot more. Okay, maybe slightly less than 20, but it's a lot more. Okay, and you wouldn't want to try for C6H14O. Okay, that's going to be madness. Right. Now, next, let us do 2.1b. Okay, so now I have propanoic acid. Okay, so I hope by now most of you are comfortable in looking at condensed structure formula. Okay, if you're not used to it, no problem, but just try. Okay, we have propanoic acid and we have hydroxyl propanones. Okay, so they are isomers with molecular formula C3H6O2. So now they ask you to draw the structure of another 2 isomers which are esters. Okay, so the question is very specific. You are supposed to draw esters. Okay, now the first thing we can do, to be honest, is simply draw out the skeletal structure. So okay, I'm going to draw the propanoic acids. Okay, and I'm going to draw the hydroxyl propanone. Okay, which looks like this. Okay, now actually these two structures, whether I draw them out or not, it will not affect anything lah, but I'm just going to draw them out, or you should just draw them out as a practice of drawing skeletal structure. Okay, I think you guys need to be comfortable in converting between skeletal, full displayed formula. Okay, full display means you show all the bonds, and as well as condensed structure formula. Yeah, once you are very comfortable in going between these three, right, then I think it's no longer an issue in organic chemistry, because I think the first thing in organic chemistry is you need to learn how to represent the structure quickly and in a decently nice way. Okay, that's all I can say. Right, okay, so I'm going to move on to draw two isomers which are potentially esters. Okay, so I think the first thing is I think I can easily swap a CH3 with a H. I'm not sure whether you will agree with me. Okay, so maybe it's actually easier if I draw out the half displayed formula, or you can call it condensed structure formula. Okay, so for it, it will be CH3. Okay, and then I'm going to draw this out for easy visualization. Okay, and then O and H. Okay, so what do I mean? Okay, what I meant is I can swap this H and this CH3, because if I swap the two, okay, I'm going to end up with this particular structure with a H here. Okay, now the left hand side become a methyl group, and then the right hand side become a methyl ester. Okay, can you see? Yeah. So I hope this method makes a bit of sense to you. Okay, the swapping. Okay, so if you recall from secondary school, right, we will say that this is actually the ester. Okay, so let's just go back a little bit to what we learned in secondary school, as well as what you might heard from me from the bridging module. Okay, so this is like an ester from ethanoic acid and methanol. Okay, so the ethanoic acid comes from here. Okay, then the ethanol actually comes from here. Okay, so this is an acid, sorry, this is an ester between ethanoic acid and methanol. Right, now can we do a bit more? Yes, we can. Okay, so now let me just erase this portion. Okay, let me just erase the highlighted portion. Okay, I'm going to highlight in yellow. Okay, can I replace this part, this whole chunk? Okay, I swap position with the H. Okay, yeah, so let's do it. Okay, so when I do it, let me just draw it, make it a bit smaller. Okay, so I'm going to have H here, and then C double bond O, and then O, and then CH2, and then CH3. Okay, did you manage to see that? Okay, so I just swap the two position, and you notice that this is indeed an ester as well. And this is actually an ester between methanoic acid and ethanol, right? Methanoic acid and methanol. Sorry, and ethanol. Yes. So yeah, so that's one way you can do it. Really, like all road leads to Rome, as I often say. So I choose to do it this way. You can choose to do it another way. Maybe you can just straight away just draw it out and then and work out from there. No problem at all. Okay, so basically the good thing about chemistry, or in particular, at least for H2 curriculum, organic chemistry, is a lot of flexibility can be introduced in organic chem. Okay, in particular organic chem for H2 level. Okay, yeah, of course in calculation wise, like the method you do is quite standard, and you need to showcase your working clearly, you need to showcase the correct statements, you need to write your units. Okay, but for organic chemistry, the way you draw a structure, of course there's some standards, but the way you arrive at your answer, there's a lot of ways you can do that. Yeah, so you don't really need to be very worried about not doing so well, or really spending a lot of time memorizing, because you don't really need to. Once you understand it, it stays with you for 2 years, if not for 1 decade. Like it will come back to you quite easily. Okay, so next let's look at two
Point 1b2, so you're asked to draw the structure of another two isomers with both alcohols and carbonyl groups. Okay, so now they kind of like fixed. I mean, your option is now fixed lah. It must be a carbonyl group and an alcohol, right? Okay, so what should I do? Maybe I can take reference from this. Okay, I can easily take reference from here, right? So I'm going to I'm just going to write it out over here. Okay, so I'm going to have a ketone drawn, okay, similar to what I did earlier on. Okay, and then with H and H and an OH. Okay, so I'm just looking at what I can do to make your life easier. Okay, maybe I will draw this out so that it will be clearer when I try to explain to you. Okay. Okay, so what I can do now is, again, I'm going to do the same thing. I'm going to swap the groups. Okay, so I'm going to swap the carbonyl oxygen with these two H's. Okay, so once I swap these two groups, I want you to notice what I end up with. Okay, this part 2 H's, the alcohol remains, okay, and then become double bond O. Okay, did you manage to see that? Okay, so this is still an okay, so of course it goes from a ketone to an aldehyde, but it's still a carbonyl compound. Okay, still a carbonyl group. Okay, then now what can I do? Okay, is there like any more things I can do? Yeah, I mean there are quite a few things you can do. Okay, different perspective depends on how you look at it. Okay, so one other thing you could do is to actually swap these two groups. Okay, so I'm just going to erase this part. Okay, I can actually swap the alcohol with the H. Okay, so when I do that, I will end up with this particular structure: OH, CH, H, H. Okay, yeah, so I'm going to end up something like that. And yes, so these are two unique isomers if you scrutinize them. Yep. Okay, how do I know? Okay, again, I think the question is, how do you know? Okay, you know it by looking at the relative position of the aldehyde to the alcohol. So in this case, 1,3 position. In this case, it's 1,2 position. Okay, and then in this case, this is a ketone. So a ketone is a unique one. So it's not considered as an aldehyde. So it's unique and different. Okay, in the way the carbon is bonded to the double to the oxo group. We call the O the oxo oxygen. Yep. Okay, so we're gonna move on to the next part, which is actually exercise 2.2. Yep. So for exercise 2.2, you're supposed to draw the skeletal formulae of all constitutional isomers with molecular formula C3H6Br2. Okay, C3H6Br2. Okay, so let's try to do that. Okay, so this is relatively straightforward. Again, some of you might ask, hey, how do we calculate the degree of unsaturation for this weird compound? I mean, not weird lah, but with halogen. Okay, so if you want to calculate degree of unsaturation for halogen, what you need to do is simply you pretend that the halogen is a H. Okay, so for example, this is C3H6Br2, right? So in this case, I can easily say that it's saturated. Yeah, because halogen, similar to hydrogen, in their organic compound, they usually form one bond. Okay, so this is analogous to C3H8. So if it's analogous to C3H8, then we can easily conclude that it is going to be saturated. And if it's going to be saturated, then in that case, it's not difficult for you to predict
the compound, right? Because remember earlier on what I did, you draw the longest chain, right? So 3 carbon, to be honest, 3 carbon I can only draw like that. Okay, there's nothing else I can do. Okay, so if it's like that, then you can do a quick count. Okay, I can put my Br on the same carbon, for example. Okay, I can do that. Or I can put my Br on different carbon. Okay, so carbon 1 and 2. If not, carbon 1 and 3. Okay, or I can put my Br on the middle carbon. So that's carbon number 2. Okay, so in that case, after you do that, then I think you can easily get the answer. So I'm just going to sketch it out for you. Okay, so now the answers would be, I'm going to get the BR here and the BR here, and then over here will be the BR here and here. Okay, and then the middle two. Okay, and then one to the left, carbon 1, and one to the right of carbon 3. And that's it, right? Okay, then next part B. So in general, how do constitutional isomers differ in their physical properties and chemical properties? So circle the correct options below. Okay, so constitutional isomers with different carbon chain. Okay, please note the keyword bolded. Okay, different carbon chain but same functional group. Okay, would have would you expect similar or different properties? So okay, usually the different carbon chain give rise to different strength. If you look at physical property in the form of boiling point, melting point, right, it usually gives you different strength because you know if you have a branch versus a straight chain, the size of the electron cloud and its polarizability will be a little bit different. So you would be expected to have different physical property. Okay, but of course, because it's the same functional group, you would expect them to have similar chemical properties. Okay, if they have the same functional group but different position on the same carbon chain, okay, would you expect them to have the same physical property? Yes, because the main carbon chain is the same. So for example, if let's say I have a straight chain um, alcohol, so one is at carbon 1, the other one is at carbon 2, right? The main carbon chain is the same, so I would not expect them to have very different physical property. Okay, so I would say similar, and then of course chemical reactivity will be the same. Okay, once you get a different functional group, okay, then I can easily tell you that reactivity will be different because reactivity is dependent on the functional group, and obviously physical property will be different as well. How do I know, and what's the simplest example? The simplest example will be what we drew earlier on, which is the ether over here. So alcohols, obviously, you would expect it to react differently from an ether. Okay, so that's what you can um, easily call the difference. And of course, alcohol can form hydrogen bonds, but ether can't. So ether is largely dispersion forces as well as PD. Okay, yep. So now let us move on to the third section, which is on stereoisomerism. Okay, now, so for stereoisomerism, right, this I do believe that would be the hardest portion in your journey for the chapter on isomerism, because stereoisomerism is something that is very new to all of you. Most of you would not have encountered it in secondary school. Yeah, so I think you have to read the definition very clearly. So basically, for stereoisomerism, right, they have the same molecular formula, okay, and the same connectivity. Okay, so maybe let me emphasize this. They have the same, okay, connectivity. Okay, same connectivity. Okay, but they differ,
okay, but they differ in their arrangement in space. Okay, so let me highlight this. They differ in their arrangement in space. Okay, so that means that they project themselves in space a little bit differently. Yeah, and in most causes, you'll be introduced to cis-trans isomerism first because it's the easiest. Okay, so why is it the easiest? Okay, number one is for cis-trans isomerism, you are told that if I have a covalent bond with restricted bond rotation. Okay, so what's the meaning of restricted bond rotation? Either they have a pi bond between them, because in order for me to rotate about a bond, right, especially if I have a pi bond there, I must overcome the pi bond before I can rotate around. Okay, but for single bond, I can rotate around freely. What about a ring structure? So again, it's the same thing. If I want to rotate around a single bond in a ring structure, it will actually result in the twist of the structure. So if you do not believe me, you can actually just use maybe a toothpicks with plasticine, right? To maybe make a structure that looks like this. So you can put a plasticine here, okay? And then you can try to rotate about this bond. Okay, you can try to rotate about any of the bonds. Let's say rotate
about this one. You can't do the rotation because once you try to rotate, right, the portions at the back will appear twisted. Okay, yeah. So that is also what I said earlier on. The degree of freedom is reduced drastically once you have a ring system. Okay, and of course, you need to have another condition. I must have non-identical groups bonded to each end. Okay, why is it that I need to have non-identical groups? Well, I mean, I hope you can agree with me on this, because let's say I have an identical group, right? For example, okay, so let's say I have something else here, BR and let's say CL. If the groups are identical, actually there is no difference between this structure, okay, and um, this particular structure. Yeah, because some of you might be thinking, right? The left structure and the right structure, isn't it just rotate about this bond? No, it's not about rotating about the bond because you can't rotate. So basically, it's just this structure, you flip it into the paper 180 degrees, and then you get this. So it's the same thing. Yeah, so these two groups are the same thing. So therefore, they are the same compound. So in order for them to be different, right? Okay, in order for them to be different, I need to ensure that one of the atom at the end is different. Okay, how do I ensure that? So for example, I replace this H with, let's say, Cl, for example, and then in the end, I will replace this H with the same Cl. So you realize that in this case, the Cl over here is opposite to the Cl over here. But for the structure on the right, the Cl is on the same side, okay, as on the same side of the double bond, CC double bond. Yeah. So from here, how do you go from one structure to the other? You can't go from one to the other because you can't do flipping. Yeah, because if you try to flip 180 degrees, right? Let's say for example, I try to flip this 180 degrees, right? I will actually end up with this particular structure. Okay, and obviously they are different. Like these two are not the same. They are not the same. They are not the same thing. Yeah. So now you realize, once I have a CC double bond, because of the restricted bond rotation, I cannot interconvert. The only way I can interconvert is to overcome the pi bond. But to overcome a pi bond, some amount of energy is required, and usually they might not be available under room temperature condition. Okay, yeah. So we give this kind of isomerism a special name. We call it cis-trans isomerism. Okay, so how do you label them as cis or trans? So basically, if they are on the same side, we call it cis. If they are on opposite side, we call it trans. Okay. Yep. So in our tutorial, I may just go on and maybe mention just a very brief mention on a little bit on easy convention, but it really depends on how much we can do in the tutorial sessions. Okay, so not to worry too much about it. Right. Okay, I think I have kind of explained some of these things, so you can just slowly read through and assimilate the knowledge. So I have actually explained this. So again, the methyl group on the same side, or you can say that the H on the same side. So we call it cis. Okay, so maybe I use a different color. Okay, H on the same side, we call it cis. Now H on opposite side, or methyl group on opposite side, we call it trans. Okay, yep. So please remember the terminology, because once you get the terminology wrong, then everything else will be wrong. Okay, so be very careful about this. And then I think earlier on we talked about this as well. Yeah, so if your N, right, you have identical groups. So actually there's no difference. Okay, you can get one from the other by just doing 180 degrees flip into the plane of the paper, or out, I mean whatever ways lah. Okay, yeah. Okay. Next, the rest are just details. You can look through them. I mean, I don't really need to go through every single bit. I might want to caution you a little bit about this formula, although by and large they are quite correct. So if there are n number of CC double bond, the maximum number of cis-trans isomer you can have is 2 to the power n. Take note of the word is maximum, but it's not always the case, because some combination may end up the same thing. We probably gonna do them in a tutorial, but I hope you don't get too confused over it. Yes. Again, this kind of the lecture notes and the lecture setting, all this, they are not meant to bore you with too much or too many details. Yeah, so a lot of things I think we'll try to cover more in the tutorials rather than going through in such a setting. Okay, yeah. Then I think here they mentioned about, let's say if I have different groups, can I still can a compound still exhibit cis-trans isomerism? Yeah. Okay. What do we mean by different groups? Do you remember earlier on, right? I was a little bit biased. I think in the example I deliberately choose the same atom, trans and then cis to each other. I did that deliberately. And do you realize that in your lecture example, they also did it deliberately? So you have the same atom cis or the same atom cis as well, or you can have them trans and then the H also trans. Yeah. So some of you might ask, let's say the atoms or the groups are all different. Can it still exhibit cis-trans isomerism? So of course the answer is yes. Right? So obviously A and B are different, right? The only way to interconvert is to rotate about the CC double bond, which is not possible at room temperature condition. Yeah. So because of that, they are non-interconvertible. You can't interconvert them freely. Yep. So you still call them cis-trans isomers, although it's not really correct. Yeah, because the word cis and trans usually have the meaning of them being the same group, opposite or same side. Yeah. So you will learn it if you do H3 or if you read on your own. I think I mentioned just now, we call it the easy convention. Okay, so if you're interested, you can Google it and then read about it. Okay, or from the textbook, which I'm going to share with you all. Okay, how about cycloalkene? Okay, I probably will not go too much into details over here, but basically just to share that for cycloalkene, if the number of carbon is less than 8, then usually you will only get the cis isomer. Okay, so what do I mean? Okay, so if you take a look at cyclopentene, right, you'll notice that the H are actually on the same side of the double bond, and cyclohexene as well. Okay, is it possible for us to draw a trans cyclo hexene? Actually, we can. Okay, so the diagram here doesn't look very nice. I'm going to redraw it. Okay, so to draw trans cyclohexene, right, what I'll need to do is I will put the H and the carbon in the trans position. Okay, and then I will try to connect the groups up. Okay, so there's already 2 carbon here. So when I connect the group up, please take a look at how it works. It will look like this. Okay, so it get twisted at the back. Something like this, but this is not so nice. Okay, so I'm going to number it, then you'll know what I mean. Okay, so this 1, 2, 3, 4, 5, 6. So this twist thing, right, means that the CC double bond is in front of you, and then the other twist was at the back of the CC double bond. Okay, this is highly strained. Highly strained. Okay, please understand this word. Okay, or you can say that it is unstable due to ring strain. Okay, so these are some of the words you can use to explain. Yeah. So usually, if you want a trans isomer, it will be for 8 carbon and above. Okay, so I can give you an example. I think the example given here is trans cyclohexene. Okay, so I will give you the example of the in cyclooctane. Okay, so I'm going to draw it over here. So for cyclooctane, right, it looks like this. Okay, so this will be the cis version. Okay, because they are on the same side of the double bond. Okay, the trans version, okay, I will draw it the same way. So again, I will fix. Okay, so my double bond is here. So my H is here. My H is here. Okay, so you notice that although there's still a bit of twisting, but it's not as straight. Okay, so 1, 2, 3, okay, 4, 5, 6, 7. Okay, so this is the trans version of cyclooctane. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay, so I hope you found this useful. I mean, if you want, you can try drawing. Remember this, in organic chemistry, it's very important to draw well. Okay, so that the reader understand what you are trying to do. Yeah, because in organic chemistry, there isn't a lot of explanation kind of question. So a lot of the question actually requires you to do drawing, especially if you do H3 next year. Yeah. Okay, so I've gone through this. Is it possible for ring structure to also exhibit cis-trans isomerism? It is kind of possible as well. I mean, it is possible as well. We will call this restricted bond rotation because you cannot rotate freely. Okay, so in our case here, you notice that the Cl, actually one is projecting up, the other one projects down, and then you can have both projecting downwards or upwards. Yeah, so if you represent this as a skeletal structure, right, it will look like this. Sorry, it will look with a cyclopentane, and then Cl projecting out towards you, the other one projecting out towards you, and then after that, the trans version will be this thing projecting out towards you and this thing projecting out away from you. Okay, so I hope you are able to sort of interconvert in that sense between structures like this and maybe structures like this. Okay, like like the difference between the cis and the trans version. Okay, and this. Okay, but the structure I've drawn is actually later on you're going to learn is actually the enantiomer for this. Okay, so actually for this particular one, I should actually be drawing the other isomer. Okay, so let me just show you the proper one, and then this is projecting. Yeah, so this is actually the version which I should draw. Yeah, because this is actually projecting upwards, and then the other one projecting downwards. Okay, of course these two project downwards, but it doesn't matter because if I flip over, it's the same thing. Okay, but of course if you want, you can still draw them out the prim and proper way. So if you want, you can just show them projecting downwards as well, although it's the same thing lah. Okay, yep. I'm going to move on to exercise 3.1. You are being asked which of the following alkene exhibits cis-trans isomerism, and then draw the cis-trans isomer if any and label them cis or trans. Okay, so I think this is pretty clear cut. Shouldn't be a major issue. Yeah, because you have two carbon CC double bond. So if I'm going to draw one of it out, it will look like this. Okay, and then you probably will be able to tell that this is actually the cis version. Okay, and then for the other one, it will be opposites. Okay, and this is actually the trans. Okay, so this is the trans. Okay, so I don't think I need to elaborate much because I think in this case, if you understood what I said earlier, you should be able to illustrate out the structure relatively quickly. Okay, and for B, let me just try to draw this out in slightly more details, should I? Okay, so I'm going to purposely put a H. I'm going to purposely draw the H out. The reason why I want to draw the H out is for you to see or for you to check out whether cis-trans isomerism is possible. Okay, so there's a BR over here. Okay, and then I have a carbon. Okay, and like this, and a H here, and a H here. Okay, number one, I need you to recognize that this is actually a 6-membered ring. So remember earlier on that for a 6-membered ring, there will be considerably amount of ring strain if I'm going to draw out a trans isomer. Yeah, so in this case, cis-trans isomerism is not possible for the ring system involving the CC double bond. Okay, then for the aliphatic CC double bond, what you notice is that the carbon right at the end, right, is bonded to identical group. In this case, it's a H. So therefore, cis-trans isomerism again is not being demonstrated. Okay, why is that the case? Yeah, because some of you might be wondering, hey, how about this particular structure? Isn't it different from the top? Okay, so like that. Let's say I draw this. No, actually they are the same thing. The top one merely gets converted into the bottom one, right, by a single bond rotation. Okay, so if you rotate around it, right, this H will be rotated down over here. Okay, so if you rotate again, you'll get the one on top. Yeah, so this is merely a sigma CC sigma bond rotation. Yeah, so you wouldn't I mean, because the rotation will happen very quickly, so therefore they can interconvert very quickly, so they are the same thing. All right, okay, so we'll move on to exercise 3.2. So for exercise 3.2, right, you are being asked which molecules have isomers that exhibit cis-trans isomerism. Okay, so I mean you are given several options. Let's try to take a look at all the options to the best of our ability lah. Okay, so now I have this C3H6BRI. Okay, so it's actually an interesting formula, C3H6 BRI. But if you recall what I mentioned to you earlier on, right? The first thing to determine whether it has cis-trans isomerism, right, is I think before you even try to draw everything out, right, please ensure that the compound is not saturated because if it's saturated, then there's no point. Okay, so if you recall what I said to you earlier on, if you treat the halogen, because halogen only forms one bond, right? If you treat the halogens like hydrogen, right, then the baseline formula here will be C3H8, which is the same as propane. So this is saturated, right? So if it's saturated, then there's no point talking about it. Do you get what I'm trying to say? Yeah, I mean, saturated compound, no point for us to talk about it because it is saturated. Okay, yep. Then the next thing is how about C3H5I? Okay, so for C3H5I, right? What's going to happen here is that we do the same thing. Okay, so we calculate. Okay, it has the baseline formula C3H6. So yep, you expect it maybe to have one CC double bond maybe. Okay, so if it has one CC double bond, right, then you realize that it's not going to. I mean, let's try to draw something out first before we even make any conclusion. Okay, so let's try to draw something straight chain. Okay, so we have a CH3 here, for example, and then maybe a H here, and then an I here, and then an H here. Now, do you see something interesting? Okay, so you get to recognize that actually it is possible to have cis-trans isomerism, because the question is isomers that exhibit. So I will purposely draw isomers that will exhibit cis-trans isomerism. I will not hit myself on the foot. So in this case, yep, 2 is correct. Okay, so 2 is correct. So I'm just going to look at the option with 2. But because option A has 1, so I will straight away eliminate option A. Okay, right. What about this? Okay, now, again, C3H4I2. So again, baseline formula C3H6. Okay, now if it's C3H6, I think it's probably a similar idea, I would say. Yeah, because what I can have, or what I could potentially have is an I here, okay, and then a C with a double one C here, and then with a H, and then with a H here as well, and then a CH2I. Okay, so does it make any sense to you? Yeah, so again, potentially I can have cis-trans isomerism because the H is trans to each other. Okay, so I hope what I've drawn make quite a bit of sense to you because I think it is by drawing that you can see things, and you notice that I deliberately draw them in such a way that I only draw the compound which exhibits cis-trans isomerism. I don't attempt to draw every single thing, because once I hit one that exhibits, right, then I'll just stop there. Okay, so again, if you're sharp enough, you realize that okay, 3 is here, okay, the rest no 3. Yeah, so if you do by elimination, which is quite funny, my answer is B. Yeah, because only B have 2 and 3 correct. Yeah, and then so therefore 4 must be correct for sure. Okay, so again for 4, right, I have the baseline formula similar to an alkene, which is propene here. Yeah, so again, can I try the same thing? Of course, you can try the same thing. Okay, so I'm just going to do that. So what I'm going to do is, again, I'm going to just draw it out with a carbon here, with a H, with a double bond here, and then an H, and then a CH2Br. Okay, so with this, you notice that I gravitate towards drawing trans structure because again it's easy to see. Of course, cis is easy to see as well. Really depends on your viewpoint. Yep. So once I drew that in, then I can straight away conclude that this compound 4 actually exhibits cis-trans isomerism, and therefore B will be the correct option which I will pick. Yeah. Some of you might be wondering, can I draw cyclic structure for 4? I mean, you can if you want, but again, it's not necessary because if you try to draw it, then I personally feel that it's just going to make things a little bit complicated. Yeah, so to do MCQ, basically it's like one shot, one kill. Okay, once I can get what I want, I'll just move on. I wouldn't even bother to keep doing and doing and doing. Yeah, of course, to check answers I should, but in this case, I already get the answers. Yeah, so I'll just stop there. Okay, then next, I have linoleic acid is an essential fatty acid in human diet. So it has the following structural formula. Well, I mean, it looks a bit complicated. Yeah. Okay. So anyway, question is, or rather, the idea is in linoleic acid, both double bonds are in the cis configuration. So the keyword here is both double bond in the cis configuration, representing the formula by the abbreviated form like this. Okay, that's fine. Draw the structure of linoleic acid. Okay, since they want us to draw it in the abbreviated form, then I mean we should just follow. So in case you're wondering what are the form, what are exactly is B, right? So B is actually this whole portion over here. Okay, and then A is actually this whole portion over here. Okay, and because both the double bond are in the cis configuration, okay, I will just draw that out in the cis configuration, right? So what I'll do is I'll first do the zigzag version. I'll put A, okay, and then I'll put a double bond like this, okay, because it's cis, right? Yeah, so therefore the H must be on the same side. Okay, so the H, therefore, if I'm going to draw in green, it will look like this. The H will be like this. Okay, and then I'm going to draw down because this is going to end up with a CH2 here. Okay, and then remember in skeletal, you try to do it in zigzag, right? Okay, so since I do it like this already, and then I'm just going to continue like this. Okay, and then this is another carbon that forms a double bond, right? Okay, and I'm going to do a zigzag as well, and this is double bond. So because it's cis, the H must be on the same side. Okay, so it must be like that, and then therefore the final B is like this. Okay, so I hope you get what I'm trying to do, and you get all the thought process in drawing the molecule. Okay, to draw the trans version, the trans, or rather all its cis-trans isomers, sorry. I'm supposed to draw all the cis-trans isomer. So again, it will not be difficult, okay, to draw the cis-trans isomer, because all I need to do is just to copy my structure here, okay, and decide. So I have cis, right? So this is cis, right? And then the next one I'm probably going to draw will be cis-trans. Okay, so to draw cis-trans, I'm going to repeat the same thing. Okay, and then over here, I'm going to draw the trans version. Okay, can you see? It can be done quite quickly in one clean stroke. Okay, I do not need to draw out the H. Just now I draw out the H is for illustration purposes. Okay, so in reality, when you draw your structures out, you don't have to draw out the H's. Okay, unless you are not confident, then you should draw the H's. Okay, then my other example, okay, I'm going to do the same thing. I'm going to start off with trans first, because just now I started with cis. Okay, so it's going to be like this, and then B. Okay, sorry, this is B, not BR. I think I wrote it quite quickly. Yep, and that's it. So one is cis-trans, and this is trans-cis. Okay, so with that, I'm done with A and B. Okay, so what's the application? You can read this on your own. So basically, it's about how our eyes work. So again, our retina is actually the cis isomer. When light gets shone on it, and then it becomes the trans version. Okay, if you are interested to understand why, you can read up on photochemistry. Okay, in particular, how the above happens. Okay, it's actually quite interesting. Alright, the final section on enantiomerism is actually the toughest.
Yeah, so I will do my best to at least showcase to you via the video lecture on how you could visualize it. But I think the best way to learn is still by having a model with you. Okay, so before I go into explaining some of the stuff, right, I thought I just want to go back to what we did earlier on. Okay, so if you take a look at one of the examples we did, I think is exercise 2 point something, right? So we have a C4H10O, and then you were asked to identify all the possible constitutional isomers, and then we went through the whole list. We got a total of 4 possible alcohols and 3 possible ethers, and then the total number of constitutional isomers is actually 7, right? Then I'm not sure whether you do notice this particular interesting looking molecule. It's actually quite interesting because I'm going to just draw out the formula to showcase to you the number of, how the structures look like. And then I want to get you to think a little bit about what are the other possibilities if I'm going to project it in space. Okay, so with that, I'm just going to erase this so that it's actually easier for me to draw. Okay, so if I'm going to draw the structure out, right, it will look like this. I have a CH3 on the left, and then I have a carbon in the middle, and then I have an OH group, and then a H below, and then a CH2, CH3. Okay, I want you to recognize that this particular compound, right, I'm drawing it in a very specific way. Again, I'm doing it deliberately. Okay, I'm going to showcase to you the fact that it has 4 different groups around one of the carbons. That is carbon number 2. So 1 group, 2 groups, and then 3 groups. Okay, and of course 4 groups. Okay, so maybe I should use a different color over here. Maybe, yeah, 4 groups. So what's so special? Okay, if this compound is square planar flat, 90 degrees, then it's not very inspiring. But you know that the carbon in the middle is sp3 hybridized, and if you understand from your VS EPR theory, this carbon is actually tetrahedral in shape. Okay, so with this particular idea, okay, I'm just going to illustrate something for you to see on CamDraw, and hopefully the visualization will help you to understand where I'm coming from. Okay, so I'm going to move on to CamDraw over here. Okay, I'm going to draw out the structure, okay, in exactly the same way or almost exactly the same way. Okay, so there's an OH on top. Okay, so I'm going to put OH on top. Going to put a carbon here. Okay, and then you realize that over here earlier on it was a CH3, right? Okay, CH3, and then as a tetrahedral center, you know that there will be a bond that is projecting towards you and a bond that is projecting away from you. Do you remember what we talked about in our earlier lecture in topic 8? Okay, so with the bond projecting towards you, let's put H there. And with the bond projecting away from you, of course, is a CH2, CH3. So I can do it skeletal or something else. It doesn't really matter. Okay, so what I'm going to do is I'm going to take this particular structure and I'm going to paste it over to Cam 3D over here. Okay, yes, so I'm going to get this particular structure and then I'm going to enlarge it a little bit for you to see. I'm going to do some bond rotation. Okay, so I'm going to rotate it in such a way that it is almost exactly as what you expect it to be. So I'm not sure whether it is obvious to you, but let me try just to make sure that the rotation makes a bit of sense. Okay, over here, something like this, and maybe like this. Okay, so can you see that I'm fitting everything in nicely? Okay, so I'm just going to put this maybe side by side. Okay, so can you see that the CH3 is now over here then the OH is on top. So this particular portion is actually on the plane of the paper over here. Okay, and then my H is actually projecting towards me, and then my ethyl group is projecting away from me. Okay, I'm not sure whether you can see that, but maybe just let me rotate a little bit. Can you see that the H is projecting towards you, towards us, or outside the plane of the computer or the screen? And then there's a ethyl group over here that's projecting away, so going behind, okay, moving away from the screen. Okay, so this compound, I'm just going to leave it as it is. Okay, now I'm going to do something a little bit unusual. I'm going to draw out its what we call the mirror image. Okay, so I'm going to write or draw a mirror plane over here. Okay, a mirror plane. Then I'm going to draw the exact mirror image. Okay, so I'll need to put a carbon in the middle. Okay, and then of course OH will still be OH, and then the CH3 will be behind, and then I'm going to have the H projecting out as well, and then the ethyl group projecting in. Okay, so I'm going to have the OH over here, right? And then the ethyl group like this, and then the CH3 over here, and then the H over here. Okay, so now I need to convince you that this is indeed the mirror image. Okay, I need to convince you on that first before we do anything else. Okay, so if you just reflect directly, so OH is over here, carbon, and then the ethyl group, okay, projecting in is still projecting in, and then the H projecting out is still projecting out, except it's mirror image, methyl group behind, and then to the left, and then it's to the right. I'm going to do the same thing to this molecule. Okay, I'm going to paste it over to Chem 3D. Okay, and then same thing, I'm going to do the rotation, and then just to show you that these two are mirror image. Okay, over here. Okay, so I'm going to shift this like this, and then I'm just going to rotate. Okay, now okay, I can't remove the H for simplicity, but yeah. So can you see that? Okay, so the H is here. It's a mirror. Okay, so imagine this is a mirror plane, and then the H is here, and then the ethyl group is projecting away. This ethyl group is also projecting away. Can you see? And then OH is up, OH up, methyl group to the right, methyl group to the left. Okay, now on paper it looks like they are the same thing, right? But I need to show you the bond rotation to impress upon you that they are actually different. Okay, so let me try to do a bond rotation like this. Okay, can you actually tell that if I try to fit the OH, carbon, and CH3 to be on the same plane, right? Do you realize that the H is now projecting inwards and instead of outwards, and then the ethyl group is projecting towards me instead of away from me? Okay, do you notice that I did not change anything? Okay, I merely do a bond rotation. Can you see I have not cheated? Okay, so let me just rotate it back to the original position again. Okay, this is the mirror. This is the okay. Okay, let me just try to fit in the original position so that you know that I did not actually cheat. Okay, yes, like this. Okay, so this is the original position, right? Correct. So OH, OH, H, and then methyl group to the left, methyl group to the right, and then ethyl group projecting away, ethyl group projecting away, right? Okay, so now to prove that they are not the same thing, or we can say that they are non-superimposable, what I'm going to do is I'm going to try to fit the OH, carbon, and CH3 to be on the same plane as this, so that there is a point in comparison. And this is also to impress upon you that they project differently in space. Okay, I'm going to do that now. Rotate like this. Okay, now can you see that after I rotate, right, I'm able to superimpose this portion, the OH, C, and CH3 directly. But if I try to superimpose them together, which I can't do it because they are at different
different windows, right? You'll notice that if I try to superimpose them, I'm not able to superimpose the H and the ethyl group, because now in the structure on the left, the H is projecting out of the computer screen, but on the right window, right, is projecting inwards. And then in this case, the ethyl group is projecting inwards, but on the right hand side is projecting outwards. Can you see that? Yes. So this is the main idea. Okay, this is the main idea of enantiomerism, which I thought I should just introduce to you before we go into the lecture itself. Okay, as you have seen from the earlier demonstration or rotation using Cam 3D, right? I'll have shown you that the mirror image is non-superimposable onto itself. So which means, for example, just now you have seen that when the original molecules have its hydrogen projecting out from the plane of the computer, the mirror image, the hydrogens will have its bond projecting inside or into the plane of the computer. And then the ethyl group is the same. Okay, so because they are non-superimposable and they only differ in their projection in space, right? We call them non-superimposable and they are different. So we give them a special name. We call them enantiomers. Okay, so normally we'll say that A is an enantiomer of B, the mirror image, or we can also say that B is an enantiomer of A. And then we call these two enantiomeric pair. Okay, we give them a special name, enantiomeric pair. Okay, and we call the particular center, we also give it a special name. Okay, so this particular center, right, we usually represent it with an asterisk on paper, okay, to help us identify it. We call it the chiral center. Okay, so normally, in order to determine whether a molecule exhibits enantiomerism, right, we need to look out for whether a chiral center exists, okay, and whether the said molecule, right, whether it possesses any internal plane of symmetry. Yeah, so enantiomerism will not be possible if it contains an internal plane of symmetry. I think it will be clearer for you later on when we have more examples. Okay, now my apologies that earlier on I used a relatively complicated example like this. The reason is just to showcase to you that in the real world it is possible. And of course, in this particular molecule, you realize that it's quite complicated because the groups are very huge. Okay, so over for the lecture example, right, we actually use a much simpler molecule, okay, with HFCl and Br. Okay, so I'm going to illustrate to you over here so that you can tell, and then it might be easier for you. So let's see, HFF, okay, Cl and Br. Okay, so of course, this is a lot cleaner, and I think it's much easier for you to tell. Okay, so we have a F over here. Okay, I'm going to erase this extra bonds because it's not necessary. Okay, so I'm going to paste this over to the windows on the left. Okay, so I'm going to okay, and then I'm going to paste the other one onto the right hand side. Okay, so right now I hope because the molecule is the molecule is smaller, so it's easier for you to see. Okay, so now what I'm going to do is I'm going to put the Br away. Okay, going to put the Br away. Okay, so the larger atom is actually the Br. Okay, so the Br is now behind, to the left, the H is up. Okay, so maybe I should rotate a bit. Okay, then can you see that the chlorine is projecting out towards you, and then the fluorine is projecting away? Okay, so I'm going to do the same thing on the right hand side. Okay, then you notice that for this particular mirror image, okay, it's the same thing. The Br is actually on the right hand side, can you see? And then a H on top. And then this Cl is projecting towards you, right? Same thing, F is projecting away from you, same thing. Okay, I will try to superimpose the two of them together, okay, by trying to fit the H carbon and Br on the same plane. Okay, so I'm going to do that over here. I'm going to rotate and then try to put it on the same plane. Okay, just going to, okay. Do you notice something different? Now, the Cl, instead of projecting towards you, is now away from you. The F, instead of projecting away from you, is now projecting towards you. Okay, there is no way I can interconvert both of them. Do you realize? Except, of course, except to break the bonds. Okay, no matter how you twist and turn the structure, you cannot interconvert. Do you recognize that? I mean, without breaking the bonds. You can rotate, etc. Okay, but I want to bring across one important idea to you, and I hope you'll be able to understand it. You'll be able to understand what I'm trying to say. Do you realize that I deliberately keep telling all of you to just keep one of the plane constant like HC and BR, HC and BR? Some of you might ask, I'm biased, why I keep one of the plane constant? Can I keep another plane constant? No problem, it's your choice. Okay, I can choose to keep the HC and Cl plane constant. Okay, not a problem at all. And I want you to notice what happens. Can you see? I keep the HC and Cl plane. Okay, so this is a direct mirror image, right? Okay, now I try to superimpose the right hand side on the left hand side by keeping this plane a constant. Okay, I'm going to rotate. Can you see? Constant plane, right? Okay, so what happens? Now the Br is projecting away, but now it's the F that's projecting away. F is projecting towards me. Now the Br is projecting out towards me. Okay, do you notice the difference? Yeah, so it doesn't matter. So let me repeat. It doesn't matter which three atoms, in this case, three atoms, you kept the plane or you put them in the same plane. Yeah, because the outcome will be the same. Okay, outcome meaning enantiomerism will still exist. So it's just a matter of perspective. Okay, I hope you found this useful. Using Chem 3D, and you can really see that it makes at least some difference in the way you visualize things. Of course, the best way is to build a model and look at it. Okay, and whatever has been explained to you over here is already incorporated in the Chem 3D and the Chem Draw, which I try to explain to you. But what is more important for you guys, right, is to be able to draw the structure in the way it's being presented. So meaning, right, you must be able to draw them two of the bonds on the same plane, one projecting towards you and one projecting away from you. Okay, and if you wish to, you need to be able to do a rotation to try to fit the Br and H on the same plane, like what happened here. And then after you do the rotation, you realize that whatever bonds that is projecting away, right, will now be projecting out, projecting towards you. Whatever bonds that's projecting towards you will now be projecting away from you. Okay, so that's the outcome of a bond rotation. Okay, yeah. So because they arrange themselves differently in space, we give them a special name. We call them enantiomer. Like molecule 1 is an enantiomer of molecule 2, or we can say molecule 2 is an enantiomer of molecule 1. And then both of them, we call them enantiomeric pair. Okay, so this is a special name that you need to learn how to call it. All right. And then we're going to move on to exercise 3.4. So we're supposed to draw the mirror image. Okay, so it's the same thing. Okay, so we're going to draw the H like this. Like this. Okay, and then we're going to have a CH3 here, and then a CH2, CH3, and then the OH, and that's it. And because there are 4 different groups, so this is a chiral center. Okay, so I hope you found it useful, and your understanding of this matter sort of increased because like when you are able to visualize, it will help you in your understanding by quite a bit. Okay, now for
exercise 3.4b, you're supposed to identify the chiral center. Okay, so it shouldn't come as a surprise because basically the easiest way is to choose those chiral center with 4 different groups. So in this case, this chiral center have this center have 2 groups, 2 hydrogens, so I won't choose this. Yeah, so I will choose this. Okay, then as I move across the middle one, you know that there's an H here, although it's not drawn. So again, this is a different group. H is different from CH3. Okay, well, once you have a cyclic system, some of the students will realize that it might be a bit challenging. Okay, actually, to be honest, the simplest way is just to number them left and right. Okay, so when I number them left and right with the same number, let's say this 1 and 1, right? You notice that for carbon number 1 on the right hand side or clockwise, this is a CH2. For carbon number 2 anti-clockwise is a CHOH. Obviously they are different, right? So because clockwise and anti-clockwise are different things, so this is also a chiral center. Okay, and we do the same for this carbon, and of course this is a chiral center as well. Alright, so I hope you found this method simple. And then of course from here, this is a chiral center. Once you have a sp2 hybridized carbon, I don't think it will ever be a chiral center because the mirror image in itself will definitely be super impossible because it's simply planar. Okay, now I just want to do one little thing before I move on to 3.2.2. Is really to convince you that you need to have 4 different groups. Okay, so right now, right, I'm going to deliberately replace one of the group with H. Okay, the Br with the H. Okay, and then I want to convince you that they are the same molecule. Okay, now I'm gonna do this. Okay, I'm gonna do the same thing, paste to Chem 3D. Okay, and then I'm going to paste the other molecule to Chem 3D. Okay. Okay. Now I'm going to orientate them in the same way. Okay. So like this. Okay. I'm going to make it bigger so that you can see. Okay. I'm going to do the same thing. I'm going to make it bigger. Okay. Now so can you see that they are direct mirror image? Okay. Now what sometimes students will do is this is what they will do. I need you to follow me very closely. If you follow what I said, right? Okay, I try to put H, C, and H on the same plane, and then I try to fit this in. Okay, I'm just going to do a rotation like this. Can you see that it fits in, right? And then some of you might be saying, hey, isn't this a chiral center? Because the F is projecting away, this is Cl is projecting away, and then this Cl is towards me, and this is F is towards me. But you forgot one thing, I can rotate them in any way I want, right? Yeah, so what's stopping me from rotating this way? Can you see? I'm going to do this. Okay, sorry, I can't do it without any destruction, so I'm just going to shift it. Can you see? Once I rotate it, right, what do you notice? They are the same thing, right? Can you see? Then you'll be telling me, but you cheated, but you rotate the other way. No problem, you can rotate in any way you want. You will still end up in being the same thing. And just now, if you do not believe me, for this particular molecule, right, if you try to rotate in whatever way you want, you won't be able to fit in. Like for example, in this case, right, if I rotate like this, the H and B are swap position, then you end up being the different thing as well. Yeah. So I think my point is, for a chiral center tetrahedral, you need 4 different groups in order to showcase enantiomerism. Okay, now for the next part, molecules with more than 1 chiral center, what are we going to do about it? Okay, if you have more than 1 chiral center, of course you will end up with you end up with the same as the to the power of n number of isomers, like what we did for our CC double bond.
the cis-trans isomerism. Okay, so for this case, like molecule 3, I have 2 chiral centers, right? So I'm going to end up with 2 pairs of enantiomer. Okay, 2 pairs of enantiomer. So I'm just going to, I'm not going to draw them out, but if you want, you can try to draw it out. Okay, then you'll be asking, how are we going to try to draw it out? Okay, so maybe in the end I still need to need to showcase to you maybe the drawing, right? Okay, so I think the first thing is for the portion on the left, right? You do the same thing. You try to project them in any way you want, because it doesn't matter based on your current situation. Okay, because number one is you're not going to name the chiral center. Yeah, so it doesn't matter how you project them, but you need to project them in a way that is to your advantage. Okay, so in this case, I'm just going to use the blank sheet to draw and showcase to you. I think it's better this way, so that you get to learn more. I mean, you actually, okay, so remember that so remember that earlier on, right, we have a chiral center C with OHCH3 H, right? Okay, so I just draw it like that. Okay, and then I have another carbon here, right? So actually the simplest way is really just to showcase them like this. This is really the best way. Then some of you might be wondering, hey, can I draw them the other way? Can I draw them like that? Can, no problem. You want, sorry, I accidentally draw the H. You want to draw, you can, no problem. But the reason why we purposely drew it out in a certain way in the lecture notes is really to showcase to you one interesting phenomenon which later on you get to see. Okay, then the next thing is, okay, I have an OH, CH3 and H, right? So OH, CH3 and H, doesn't matter how you put it really. Yeah, really, don't worry about it. So OH, CH3 and H. Okay, then what's the other side? H, CH3, Cl. Okay, H, CH3, Cl. Yeah, and that's it. Yeah, then you can just draw the mirror image and you're done. Okay, so then you say, wow, it seems easier than to meet the eyes, right? Okay, I mean, yeah, I'm just going to draw it out like okay, like this. Sorry that the drawing isn't very nice, but I have to squeeze in Cl. Okay, and then I have a single bond here, and then project, okay, and then after that I have a OH, and then a CH3, and then a H. That's it. Okay, then what about the other structure? Okay, so for the other pair, right, because these two are direct mirror image, right? So for the other pair, all I need to do is just to change the chiral center for one of them. Okay, do you notice what they did over here? Yeah, what they did over here is they keep this chiral center, okay, but they swap these two groups. Okay, then you ask why. Okay, how about this? I'll leave it to you. I'll leave it to y'all to go and think about why. Okay, yeah. I think the easiest way is probably to teach y'all the naming, but I don't think I want to go there. Okay, so yeah. So the simplest way is you draw everything else the same. I'm not going to redraw, and then I'm just going to swap these two groups. Okay, so after I swap these two groups, I will end up with, sorry, I forgot what the groups are. Okay, ClCH3 and then ClCH3. Okay, and that's it. Okay, that's all I need to do. Yep. Okay, then you'll be wondering, right? Why did they purposely draw it in a certain fashion? Okay, later on, we're going to showcase something called internal plane of symmetry, which you're going to see. Okay, so because if I do a quick count, there are a total of 4 so-called stereoisomers, right? Yeah, so this fits well because the total number of stereoisomers is 2 to the power of 2 because 2 chiral centers, so I'm going to get 4. Okay, but is it ever possible for me to have 2 chiral centers and yet I only end up with less than 4 stereoisomers? Yes, it is highly possible. Okay, how is that the case? Okay, so here I'm going to show you. Okay, although I think it's also in your lecture notes. Okay, I'm just going to illustrate to you this little example. So let's say I have a compound, right? With the same group on the left and right. Okay, so I have a OH, a CH3, and a H. Okay, so I'm going to use the same example. Okay, I'm just going to erase the groups. Okay, so I'm going to put in the OH, the CH3, and H. Okay, and then what did you notice? Okay, sorry, it's a bit messy. Okay, you notice there's an OH here, there's a CH3 here, and a H. And then did you notice something amazing? I can actually superimpose the two of them together, you know. Can you try to use your eyes, right? I mean, use your eyes to imagine that if you lift this particular structure up and then you try to put it here, it's the same thing. If you realize that it's the same thing, then you have successfully understood one important concept in particularly in chemistry, in organic chemistry. It's called internal plane of symmetry. Okay, so the compound itself, right, has an internal plane of symmetry. What is the internal plane of symmetry? So if you look at this green line, right, imagine it's a plane, right? So this is like a plane, internal mirror plane inside the compound. So can you see the OH, CH3 like that? Yeah, so if you have an internal plane of symmetry, right, the two compound is the same. So it doesn't, so this particular chiral center, right, this particular enantiomer doesn't exhibit enantiomerism. So we call this a meso compound. Okay, it's just a special term lah. So a meso compound is a compound with an internal plane of symmetry. So please take note of it. Okay, so I repeat, a meso compound is a compound with an internal plane of symmetry. Okay, so that's very important. Okay, then the next portion is, so if this is 1, so do we call them 1 or 2? So it's 1. Okay, then the second, if I just swap two of the groups, in this case, I'm just going to draw out another pair. Then you realize that this particular compound, okay, sorry, I should write red. If I put a CH3 here and a H here, and then a H here and a CH3 here, right? These two will no longer, they are no longer meso because they no longer have an internal plane of symmetry. Do you notice? If I try to draw an internal plane here, right? They're actually different. Okay, so we will count them as a unique pair. So that means that if I have two chiral centers where one of the enantiomer can showcase have a sorry, one of the enantiomer have an internal plane of symmetry, right? Then the total number of stereoisomer is no longer 2 to the power 2 equals to 4. Okay, so it's actually 2 to the power 2 minus 1 equals to 3. Yeah, because one of it is being repeated, or rather the mirror image and itself is the same molecule. Okay, Ken? So, yep. So over here, I think I've explained quite a bit of things already. So we have a meso compound here, which I think you can easily try to understand what I said to you. If it's still unclear, you can always relook at the lecture. You can read through the lecture book, revisit the videos if you want to, or you can just ask me during the tutorial sessions. Okay, so earlier on you have seen molecules with one chiral center where the mirror image and itself are non-superimposable, and you have also seen molecules with two chiral centers where there could be two possibilities. So one of it, mirror image and itself are non-superimposable. The other possibility, mirror image and itself, despite having two chiral centers, they are superimposable. And the reason being, it has an internal plane of symmetry. So you might be thinking, is it a criteria to have chiral centers in order to demonstrate non-superimposable mirror image? Or
do I really need to have a chiral center for the mirror image to be non-superimposable with myself? Okay, so of course the answer is no. And we have a little extension here. We showcase to you an example of a molecule without a chiral center, but its mirror image and itself are non-superimposable. Okay, so this molecule, it has, I mean, at first glance you might think that it's an alkene, but it's actually not an alkene because it contains two CC double bonds bonded to the middle carbon. Okay, so you realize that the middle carbon is actually sp hybridized, and the one at the side is actually sp2. Okay, so if you simply just look at this particular diagram, right, for the carbon to be sp2 hybridized, that means that it will have a unhybridized p orbital over here. Okay, and of course, in order for it to form a pi bond with the sp hybridized carbon, the sp hybridized carbon must use one of the p orbital to form pi bond with it. Yeah, so if you want to take an arbitrary axis, so for example, if you want to take this to be y, along this direction is x, and then into the plane as z. Okay, so you can say that both of them are using the unhybridized pz, or to be more specific, 2pz, sorry, 2py, not z, 2py for overlap. Okay, so this is using the unhybridized 2py for overlap. Yeah. However, you will notice that because the middle carbon is sp hybridized, when it overlaps with the next sp2 hybridized carbon, right, it can't be using the same 2py because it has already been utilized. So in this case, it has to utilize the other p orbital. In this case, it's actually the 2pz over here. And if it uses the 2pz, then that means that the other sp2 hybridized carbon must use its 2pz to overlap with it. Yeah, and you realize that these two p orbitals are orthogonal or perpendicular to each other. Yeah, so that means that if we are looking at the 2py orbital overlapping on the plane of the paper or on the plane of the screen, then that means that the Cl and the H, the Cl will be projecting inwards, the H will be projecting towards you because it needs to maintain a trigonal planar geometry. Okay, so that also means that the other carbon, the H and the Cl are on the plane of the paper because the 2pz orbital actually points into the plane of the screen. Okay, and because of this, it created a scenario where these two H and Cl, they are orthogonal to the other H and Cl. Yeah, so if I'm going to place my eyes, okay, so maybe just let me erase part of it. If I'm going to place my eyes over here, okay, then I will be looking at the Cl over here. So let's say I'm going to draw a rectangle, okay, then the H will be here, okay, and then behind it, okay, so I'm going to use another color. So behind it, the H will look like this. So the H will be here, and then the Cl will be here. Okay, you can see that they are orthogonal to each other. Okay, then with that coming into the picture, you realize that the mirror image, which is this, and itself are non-superimposable. Yeah, because if I try to flip the mirror image around, meaning I turn it 180 degrees into the plane of the paper, either clockwise or anti-clockwise, I'm going to end up with this. Okay, so I'm going to draw it out above. So I'm going to end up with the H here, the C, the Cl, double bond C, double bond C. Okay, however, because I flip it 180 degrees, right, the H originally points towards me, now it will be pointing away from me. And then the Cl originally points away from me, now it will be pointing towards me. Okay, so you see that these two are actually non-superimposable. And because they are non-superimposable, we say that it exhibits enantiomerism.
Okay, yeah, so this is like I wouldn't say it's an exception. Okay, I would just say that as long as the mirror image and itself are non-superimposable, then these two will demonstrate enantiomerism. Okay, the only thing is that the most common case for enantiomerism is you have a chiral center. Okay, so I hope that might clarify some of your doubts. Okay, now let's look at exercise 3.5. You are supposed to draw the enantiomers of butane 2O and indicate the chiral centers. I think I've done this earlier on in my earlier examples. In this case, I'll just draw it. Yeah, so again, you decide how you want to place your groups because it doesn't really matter at the H2 level. So in this case, if I choose to place my group, my larger group on the vertical, I mean above, then I'm going to draw a carbon here. Okay, then I think the easiest way is always to position the groups nicely. Okay, okay, so I just draw the hash and the wedge, and then I draw the hash and the wedge. Okay, and then the other group CH2, CH3. Okay, so now it's really up to me how I want to draw the group. So I can put an H here, I can put an H here. Okay, then I can put the OH. Okay, then I can put the OH, and then maybe the CH3, and then the CH3. Okay, so the easiest way is to draw out your chiral carbon and then put the hash and the wedge and then the other two bonds on the same plane of the paper and then just plug the rest of the groups in. That will be the easiest. All right. Okay. So next question number 2. You are supposed to identify the chiral centers in pentane 2,4-diol molecule below. How many stereoisomers does pentane 2,4-diol have in total? Yeah. So I think same idea. So first, we need to look at each particular center. I mean, those with 4 different groups, so-called lah. Okay, so I think we can easily identify these two bonded to the OH. Yeah, because there's a H here, and of course there's a H here as well lah. Okay, so in this case, these two are actually chiral centers. Yeah, so if these two are chiral centers, yeah, we can go through this particular exercise. So we can have the 2OH projecting towards us. Okay, and then of course the H will be projecting away from us. We can just draw this in first. Okay, and then if you try to draw the mirror image, okay, if you try to draw the mirror image, then you realize maybe something a little bit surprising. Okay, so I'll leave you to discover on your own without hearing me for now, but I think you are listening to it. Okay, we have a H. Yeah. Did you actually recognize that the mirror image, okay, maybe I just call this molecule 1 and itself are actually the same thing? Yeah. Okay, because I mean, if you're quick enough, you realize that there's actually internal plane of symmetry. Yeah. Yeah, so because of that, I wouldn't call them 1 and 2. I'll just call them 1. Yeah, because both of them are the same thing. Okay, so that's count as 1. And then of course, if you recall what I did just now, I can keep one chiral center. Okay, so I can keep one chiral center as the OH, and then the other one I will project away. And then I'm going to incorporate the H now. Okay, so in this case, I hope you can see that the mirror image and itself are actually non-superimposable. Okay, so maybe take a bit of time to draw it out and check out for yourself. Okay, so these two are clearly mirror image of each other, because if I try to flip this into the paper, okay, 180 degrees. Okay, so what I'm getting would be, I'm going to draw it here. Okay, so if I'm going to label this carbon as 1, 2, 3, 4, 5. Okay, if I flip over this will be 1, 2, 3, 4, 5. Okay, so in this case, the OH originally point towards me, now it will be pointing away from me. Okay, and then the H will now be pointing towards me, and then the OH originally points away, now it will point towards me, and then the H will point away from me. Okay, so if you just check out this structure and this structure, you realize that at the chiral center, are actually swapped. Okay, the key groups are swapped. And of course, the key group, it depends on which group you are talking about. But whatever the case, whatever perspective you take, there will be two groups that will be swapped. Yeah, so obviously these two are an enantiomeric pair. Yeah, so if we count them as 2 and 3 here, so there's 1, 2, and 3. So there will be a total of 3 distinct stereoisomers. Okay, so if you want to look at the relationship, 2 and 3 are an enantiomeric pair. Okay, so I hope this exercise actually showcase to you that it's actually not that difficult to draw them. I mean, one way, if you have just one chiral center, I think this is the standard representation you need to have. But if you have 2 or more, then I think a representation that is like that and is unambiguous will do the trick. Yep. Okay, gonna move on to the next part. So for properties of enantiomers, they have identical and largely identical physical and chemical properties, because the only difference they exhibit is the way they project themselves in space. Okay, but one little thing which I think we need to take note of, and it also represents its historical name, is this optically active part. Yeah, enantiomerism used to be called optical isomerism, and the reason it's called optical isomerism is because they rotate plane polarized light. Okay, yeah. So for example, if let's say this is a polarizer that only allows light to pass through in this vertical axis, right? Yeah. So once you pass it through the sample, this particular plane polarized light will be rotated at a certain angle. So either clockwise of a certain angle plus alpha, or anti-clockwise at a certain angle minus beta, something like that. Okay, so if you have an equal proportion of each isomer, so they must be the same isomer, each enantiomer, which means they must belong to the same compound. And what here means is that, for example, like this and this. Okay, so if one rotates, let's say this rotates clockwise by 30 degrees, then the other one must rotate anti-clockwise by 30 degrees. And if you have an equal proportion of both of them, then you're going to end up not rotating the plane polarized light at all. Yeah, because they cancel each other out. Yeah, so because of that, we call this a racemic mixture. Okay, so please learn the spelling of this term, a racemic mixture. Yeah, so when the sample is able to rotate plane polarized light, we say that the sample is optically active. Yeah, if you have a racemic mixture, or you have a chiral molecule or a meso compound, which does not rotate plane polarized light, we say that the sample is optically inactive. Okay, of course here we are looking at the extreme situation because a racemic mixture is an exact 50-50 mixture of the two. So let's say if you have a slightly different proportion, then you will rotate a little bit more either to clockwise or anti-clockwise, depending on which one it has a greater proportion, which enantiomer it contains a greater proportion. Okay, yep. And then The optical activity of a sample can be measured using a polarimeter. I think I kind of like give you a little bit of an introduction just now over here, although the drawing isn't very nice. So yep, you have a plane polarized light. It oscillates in this direction. Okay, so eventually it will be rotated at a certain angle. Okay, yep. So you have a polarizer here which allow plane polarized light allow lights to pass through, resulting in plane polarized lights. Okay, if you are wondering how the optical activity is being measured using a polarimeter, I have a YouTube video to showcase to you. Unfortunately, I think in our school lab, it might be a bit more difficult to perform related experiments. Okay, so of course, if it's possible, then we will let you try out someday. Yeah, but before I show you the YouTube video, maybe you just want to take note of some of these historical terms. So if the enantiomer rotates the plane polarized light in a clockwise manner, we call it dextrorotatory. Okay, in this case, came from a Latin word, dextro means right. And then we put a plus as the prefix. If the enantiomer rotates plane polarized light anti-clockwise, we call it levo rotatory. Levo here means left, so we add a minus to the prefix. Okay, there is actually a IUPAC convention of naming the enantiomer. We call it the RS configuration, but we will not be covering this for H2. So if you're interested, you can take H3 next year, or you can read up on your own. Yeah, but it's not something that is too difficult to pick up. Yeah, but maybe one more thing I would like to stress is that the R or S configuration is not related to whether is it dextro-rotatory or levo-rotatory. Okay, so without further ado, I will showcase this particular video to you so that you know what exactly is going on. Okay. Is that light to shine through only one direction? So when one of them here, this is what you see, tells me that the light is moving in this direction, which is currently horizontal. Both of these are the same. So if we look at them, see through it over there, and if I look together, it's a little darker. Yeah, so basically what he said is that the light can only go through in a horizontal fashion. Okay, so that's like a polarizer. Yeah. But if I turn it into 90 degrees, I shut out the light, and then there's what's happening is the light is going to be in horizontal from one filter, and this direction, and this direction. So let's see how these things to do and really this experiment. Watch this fascinating so what I have here is just a solution of a test tube, just less light on it, facing the bottom. So another filter, okay, so in the same direction, straight as we saw earlier. Take this filter line, rotate it by 90 degrees. When this line gets completely extinguished, this is going to be just the light this line through and this one's not this direction. Okay, so earlier on, he actually used water, and then obviously water is not chiral. Yeah, so you can see that the light passes through it, and then when he rotates the other polarizer 90 degrees, it gets cancelled out. Okay, so now he's going to test it out using another, another sample. Okay. Okay, he's using sucrose. Yeah, so if you heard him, he mentioned that the fascinating property of chiral molecules is that they are able to rotate plane polarized light. In this case, for sucrose, it rotated to the right. Okay. Okay, so I'm going to fast forward. He's showing the R carbon and S carbon, so they are an enantiomeric pair over here. Okay, I'm going to move on. Okay, so these are pure compounds as he mentioned. So we'll take a look at the properties. Yeah, so notice that at 9 degrees, the light is still passing through, unlike water, where it's totally cancelled out. Yeah, so it behaves relatively similar to sucrose. And then take note of how he rotates his filter. Okay, he actually rotated it to the left. I think you need to remember this. I mean, not remember as in remember for exams, but remember it so that later on we can do comparisons. Okay, so he's putting in the other enantiomer. Watch it. Yeah, you notice earlier on to the left becomes brighter. Now to the right, diminish, right? So if you compare with R carbon, yeah. Yeah, so you notice that they rotate plane polarized light in opposite direction to the same angle. I mean, okay, they are not measuring it here, but you can roughly tell that the angle is about the same. Of course, you need a more accurate machine or polarimeter to measure, but in this case, I think for demonstration purposes, this will do the trick. Okay, I think that's about it. I'm just going to move back to the slide. I mean, to the, yeah. Okay, so pretty much I think that's about it. You can try this out on your own if you have a sunglasses. Okay, then yeah, you can see. I mean, you can demonstrate a similar effect as what we had earlier on. Okay, so enantiomer have identical chemical properties except in their interaction with another chiral molecules. But we will not go into deep details for H2. So if you want to learn more, you can always read out more from the textbooks. Okay, so because of that, and the human body being a chiral environment, right, it will respond differently to the different kind of enantiomers, and that's why it is important for drug to. I mean, it's important for you to make the correct enantiomer of a certain drug that you are taking, because if not, I mean, worst come to worst, the other enantiomer does no harm to you, except that you're just wasting the dosage. Yeah, but in the worst case scenario, it will poison you, and then it's going to result in unwanted circumstances. Okay, so I think this diagram here shows you the interaction between one of the enantiomer, which is R-ephedrine, with the enzyme active sites, but the other enantiomer will not be able to interact appreciably. Okay, you can see that if I put this particular enantiomer in a certain orientation, this portion interacts here, the OH interacts here, and then the H it's somewhere here, and then after that this amine group is somewhere here. Okay, but if it's the enantiomer, although the phenol ring and the H seems to be able to fit in. Oh, sorry, I should be using the seems to be able to actually fit in. Yeah, but the OH seems to be interacting with the wrong receptor. Okay, and then of course, I mean, or you can say it's the wrong substrate forming the wrong complex, and then the other part also interact with the wrong receptors. So in this case, because it interact differently with the active sites, then if I'm using the wrong enantiomer, then I'm not going to expect any form of reaction to take place, or any form of enzymatic reaction to take place. Okay, I will not go through this, but it'll be good for you to read the story of thalidomide. Okay, so there are a lot of videos on it. Please go and read it or watch it. I think recently I think 2 years ago, the pharmaceutical company agreed to pay the patients a huge sum of money, and they finally admitted to their so-called wrongdoings. Okay, you can read more about it. Maybe it can be a good GP topic for discussion as well. Okay, and this portion is on kinetic resolution. I will not go into detail. So basically, it teaches you, or it showcases to you, how the enantiomers are being separated. Okay, so for example, I have a racemic mixture of mandelic acid enantiomer, and then I react it with a pure menthol to form this particular ester. Okay, and you realize that only one of the enantiomer will react with it fast enough to produce the ester, and then in the process, when I hydrolyze the ester, I can get the pure mandelic acid. Okay, so you realize that over here, the OH group is either pointing towards you or away from you. Yeah, but it's difficult to separate. So in order to separate it, what I can do is a process known as kinetic resolution, where one of the enantiomer will react a little bit faster to produce the ester, and then I hydrolyze the ester to get back the pure mandelic acid. Okay, and I think we have roughly talked about that earlier on as well. So to calculate the total number of enantiomers, you need to count the total number of chiral centers, and then of course you also need to check out whether there's any meso compounds. Okay, then if you also have a CC double bond in the system, then you need to incorporate the CC double bond in as well. Yeah, so in our case here, in order to calculate the total number of isomers present, so what we'll do is we'll just take a look at the chiral center. So there's one chiral center over here, and then we have 2 CC double bond. Okay, so a total of 8 stereoisomers. Okay, so just take note of it. Be very careful not to wrongly identify, because all these group right at the end, all this carbon right at the end, sometimes it can easily be mistaken to be chiral centers. Okay, so just take note of it. Okay, so finally we have the last two exercises. 3.6. Consider a compound with structural formula of this. What is the total number of stereoisomers, and then draw the structure of each stereoisomers. So I think first I will draw a skeletal structure for this compound. Okay, so we have a CH3 with a CH. Okay, and then a CH with a CH3, and then an ethyl group. So clearly there's one chiral center here. Okay, and then there is the CC double bond which can showcase cis-trans isomerism. Yep. So in order to showcase the enantiomer and the cis-trans isomers, we should show both at the same time. So you decide which one to do first. So I can show the trans version, okay, with the methyl group projecting towards me, and then the H projecting away from me, okay, and then mirror image, I can have in this case the H projecting away from me, the methyl group projecting towards me, and then like this, okay. Then after that, I will then swap and give the cis version, okay. Same story, H projecting away, and then now the H projecting away as well, and then this methyl group, okay, and that's it. So a total of 4 stereoisomers. Okay, then the final part, what is the total number of stereoisomers for the following compound? So again, same old story. How many chiral centers? 1, 2. Okay, the CC double bond cannot showcase any form of cis-trans isomerism because number 1, this is within a 6-membered ring, and then number 2, the 2N, we call this a terminal alkene. So a terminal alkene will not be able to showcase cis-trans isomerism because the terminal carbon have identical H bonded to it. Okay, so a total of 4 stereoisomers. Okay, and then the drug cortisone has the following formula. In addition to those chiral center marked with the asterisk, how many other chiral centers are present? Okay, so we can do a quick count. Just look at those with 4 groups. Okay, bonded to 4 unique groups. So over here, I think there's a clear-cut one over here. So that's 1, and then there's a CH3 here, and then these 2 portions are different. So 2. Okay, the other 2 are all CH2s, so we don't bother CH2s, and then maybe 3. And that's it, the rest are CH2s, and then the other 3 are already identified. Okay, so I'll choose 3 as the answer. Alright, so that's the end of isomerism, and please look out for the next video on alkane.